Hi, ladies and gentlemen. We're going to take a look at the last section in Chapter 6 today. This is section 6.3. Our emphasis today has to do with symmetric matrices and positive definite symmetric matrices. So let's jump right in. This is the third of what's going to be a little bit longer video because we have a lot of content to cover in this particular section. Starting at the beginning then, what we have is we see that one of the most important results that we leverage basically through all of chapter 7 and for a lot of applications of linear algebra is that a symmetric matrix is going to have real eigenvalues, always has real eigenvalue, and orthonormal eigenvectors. Of course, they're orthogonal, but eigenvectors, any scalar multiple of an eigenvector is an eigenvector, so we can turn them into unit vectors. These properties are incredibly powerful for us. The ability to guarantee real values so that we know we have invariant subspaces, and those invariant subspaces are orthogonal to one another. It would be great if we had every matrix as a symmetric matrix and we could guarantee these properties were working in our favor. So, reviewing the diagonalization conversation from last time, we know that because we have orthogonal eigenvectors, that we're our eigenvector matrix, which we were calling X last time, and Strang has just reverted back to his standard notation, which is the Q whenever we have an orthogonal matrix. But we're able to write the symmetric matrix in the following decomposition. This makes the change of basis conversation that much easier. So when we're applying S to Z, we end up with Q lambda Q transpose Z, and this is the change of basis into that orthonormal basis. But the beauty is that calculating the transpose is really easy compared to calculating a typical inverse. Continuing on then, we have some results here about positive definite matrices. So a positive definite matrix is by definition a matrix that has all positive eigenvalues. And associated with that, we're going to have positive pivots and what he calls the upper left determinants. So not only the determinant of the matrix itself, but all of the upper left determinants, and I'll show you what those are also positive. The energy test is one of the more important tests, and this is the situation where we're going to test to make sure that the energy is greater than 0. That's going to give us a positive definite matrix as well. The last thing he talks about is positive semi-definite. That's the same as positive definite, except we allow for a 0 eigenvalue. So it's possible that instead of all of the equalities being strictly greater than, they could be greater than or equal to, for example, the energy test could be greater than or equal to, when we write this down, we have X vector transpose Sx. And in the case where it's greater than or equal to 0, that would be positive semi-definite. And this means that we have a singular S matrix, and we'll talk more about this. And a singular matrix always has at least one 0 eigenvalue. That's all part of the conversation. So a lot of the material up front here, you just read through because it's repetition of the things that we've talked about previously. So the big items, as we talked about, are the fact that we have real numbers for the eigenvalues. We have the eigenvalues, and they're going to be real. Also, we have eigenvectors, which are going to be orthogonal to one another. We've already talked about that. For the orthogonality conversation, then I will just steer you back to chapter 4. In chapter 4, we had an extensive conversation about what orthogonal matrices are and how much of a benefit we have when we have an orthonormal basis. Remember, one of the big things is the unnamed theorem. And the unnamed theorem tells us how we can decompose any vector into an orthonormal basis because the coefficients are easy to find. And we'll take a look at an example of that. And what he ends up with here finally is what he calls the spectral theorem. The spectral theorem, every symmetric matrix is something that we can diagonalize. It's something that we can always write in this form up here. We can always write a symmetric matrix in this way. So, of course, we don't have any proofs that we're doing in this class, but as we've discussed previously, there's information to be gleaned sometimes from the proofs to help us better understand what's happening, and that is certainly the situation here. He makes the following point. S is symmetric, and because S is symmetric, the column space is equal to the row space. So I've put this graphic here, which is the 4 fundamental subspaces, just to highlight the point that, hey, we have, in this case, we have S, which is mapping, and think about it. It's always going to be symmetric, so it's going to be mapping Rn to Rn. Symmetric matrices are square. They have to be square. So you recall, given some matrix A, and it doesn't matter what it is, n by m, A transpose A is going to give me a symmetric matrix. Right? In this case, it will be an m by m symmetric matrix. And if I take A times A transpose, we're going to end up with a symmetric matrix that is n by n. Obviously, they're not necessarily the same symmetric matrix, but they are always symmetric. So any matrix that we have, we can multiply it by itself via the transpose and come up with a symmetric matrix. So what he's highlighting here is, yeah, it's a symmetric matrix. Moreover, the actual column space of S is the same as the row space. They're both the column space. And that means that the null spaces are also going to be the same vector spaces. This provides a lot of structure to the symmetric matrices, and it's what leads to the conclusions that we can draw for symmetric matrices. We'll leave you to read through the rest of the proof. You might find something in there that is beneficial. And now what we're going to do is we're going to look at positive definite matrices. So the first and foremost of our definitions for positive definite, the following: a positive definite matrix has all positive eigenvalues. So the eigenvalues are real and they are positive. So this is different from being symmetric. We can have symmetric matrices that are not positive definite. And in fact, a lot of symmetric matrices are not positive definite. So just because it's symmetric does not guarantee this property. We have additional tests that we have to run, and Strang's going to run through 5 equivalent tests, and we're going to talk about each of these. This first test, if you will, is not so much a test as the definition. The definition of being positive definite is that we have all positive eigenvalues. So Strang provides us with some examples here that we want to look through. Importantly, he provides us with an example of positive semi-definite. So this is the case where, and we'll just highlight it, you can see that we have a 0 eigenvalue. So we have a triangular matrix, or in this case, a diagonal matrix with the eigenvalues of 2 and 0. This is a positive semi-definite because we could end up with the energy equaling 0. And that really is the segue into our next conversation, which is about this energy test, which he will tell you is probably the best and most important of all of the tests that we have. So what the energy test is actually named for, and that's why I've written a little note here on the side, is it's named for kinetic energy. So you're used to this equation here. Kinetic energy is 1/2 mv squared. You've seen that in physics class. But what happens when I have a matrix? So I have kinetic energy is equal to 1/2, and now I have a mass matrix. So instead of an individual item, and this comes up frequently, we have a mass matrix that contains a whole series of masses that are connected with springs or springs and dampers. This applies to electric circuits. There's a lot of applications here. And we want to multiply by v squared. Well, each of the items that's in the mass matrix has a velocity, so we have a vector. But we can't just write down v squared. There's no such thing as taking a vector and multiplying it by itself. And so how do we do this? Right? This situation here is certainly not correct. So what we're going to do is we could take the dot product. The dot product between with the velocity vector would give us something that is a constant, and we would multiply that constant through the entire mass matrix. But that doesn't feel right. The different items in the mass matrix have different velocities. Giving them all the same multiplier doesn't seem to make sense. And that's correct. That's not what we want to do. What we're going to do instead, and this comes up frequently when we're talking about quadratics in linear algebra, is we're going to end up pre-multiplying by V transpose, and then the mass matrix, and then pulse multiplying by V. That is the correct way to apply a vector squared. So this is the kinetic energy representation when we have linear algebra problem, when we have a mass matrix. And that's all that he is saying right here. S is positive definite if, and it's X transpose times S times X, where of course X is a vector, is positive for all non-zero vectors. So the energy test, we are taking X times S times X, X transpose times S times X, and that has to be greater than 0 for all X vectors that are in, and we'll call it Rn, we'll say that S is n by n. So that seems onerous. How are we possibly going to check all the vectors? That seems ridiculous. Well, we'll talk about that in just a minute. So you definitely want to read through his conversation here. He provides a good example. Of how we can write the X transpose times S times X and what it actually is going to look like in a two-dimensional case. It helps us build our intuition as to what's going on. So it turns out that we don't need to check all of the X values. And the reason we don't need to, let me grab this and bring it front and center, is because we know from before that given the Q, and remember the Q's here are, those are the eigenvectors. So if we have any vector X that we just grab from Rn, so we have our X vector is in Rn, so we grab any X vector and we can write it as a linear combination of the eigenvectors. Not only can we do that, but it's easy to do because of the unnamed theorem. Do you remember the unnamed theorem and what it tells us? It tells us how to calculate the coefficients. Because the Q's are orthogonal to one another, and more specifically orthonormal, then we know all it takes for us to calculate the coefficients is to apply the dot product between X and the particular eigenvector. So we can take any vector in Rn and break it down as a linear combination of these eigenvectors. Because that's true, all we need to do is check the eigenvectors. We use the energy test and apply it to the eigenvectors, and if it's true for the eigenvectors, then we know it's true for every vector in Rn. And that's what he shows us here. Let me just circle it. This is the conversation. And the reason that this works out so cleanly is because when we take the representation of a vector and we do X transpose times S times X, we end up canceling out all of the Qi's and Qj's that are orthogonal to one another. And this is why it's such a clean test and such an easy way for us to check to see if something is positive definite. So let me just highlight where he says that. But more is true. If every eigenvector has positive energy, then all non-zero vectors have positive energy because we can represent them as a linear combination of the eigenvectors. So moving on, we have 3 more tests. Test number 3 is, and we'll finish up with this near the end, but let me just write it down. We know that given any A, and we just talked about this, A transpose A is symmetric. And AA transpose is symmetric. It does not matter what the dimensions of A are. The amazing thing is that if we have a positive definite matrix, so we have a symmetric positive definite matrix, the reverse is true. We can take the positive definite symmetric matrix and we can pull it apart into A transpose times A. So this result, which is not necessarily true in general, is true for symmetric positive definite matrices. We'll take a look at that at the end. Then tests 4 and 5 have to do with the determinants and the pivots. So let me talk just a little bit about the determinants. I'm going to grab, this is our test matrix right here, and let me just copy this over. And what I want to do is demonstrate how we find these determinants. So let me move it a little bit farther over here. So when he talks about the upper left determinants, and he draws a nice picture for us here, but I just want to show you in a different example. The upper left determinants, what he's saying is go over one row and one column and look at the determinant of that square matrix, which in this case, of course, is just 6. So he calls that D1 is 6. Then, second row, second column, grab that 2 by 2 matrix and find the determinant of the 2 by 2 matrix, which we can see is 42 minus 1, which is 41, also positive. And then we just keep doing this. Of course, in the 3 by 3 example, we are only going to have 3. Moreover, D3 is equal just to the determinant of S. And we could calculate this using the pitchfork method or whatever, but this turns out to be 216, also positive. So because all of these upper left determinants are positive, the matrix is positive definite. It's satisfying the same condition. The last test has to do with the ratios. The ratios of these determinants give us the pivots. So that's something new that we haven't talked about before. So the first pivot, of course, is just going to be the D1 value because that's just 1, 1. So D1, that's the pivot in the 1, 1 position. So let me call it pivot 1, 1. Then the ratio D2 over D1 is the pivot in the 2, 2 position. Because the matrix is square and because it's non-singular, if it's positive definite, then it's invertible, then we know that the pivots are going to occur on the diagonal. We're not going to have to do any pushing over in the columns. We're always going to have non-zero pivots in order for us to have an invertible matrix. And then similarly, continuing on, we have D3 over D2, and that's going to give us our final pivot at 3, 3. So this ratio, which he talks about right here, is equal to the pivots when we do the LU decomposition. Because the D's are positive, obviously the pivots are positive, and vice versa. If we do LU decomposition and we see that all of the pivots are positive, then we know we have a positive definite matrix. Again, as long as it was symmetric to start with. So those are the tests. And what I'm going to do is just give you a little bit of a demonstration in MATLAB talking about the 5 tests and show you some different commands. So I have the S matrix here. I've opened a live editor and you can see this is our matrix. Let me expand this a little bit, make it a little bit easier to see. So we are going to just start right out with XL is equal to eig of S. So the eig command gives us the eigenvalues. The first matrix that we put in here is going to be the eigenvector matrix. So in our particular case, I'll put in Q because S is symmetric. And because it's symmetric, what we're going to do is we're going to come up with orthogonal eigenvectors. So here is the set of orthogonal eigenvectors, and this is the MATLAB command. It gives us a diagonal matrix with the eigenvalues along the main diagonal. From the eigenvalues, we can see we have a positive definite matrix. Then we can take a look at what these vectors are, and we can see that they are certainly orthogonal. If I take Q1 dotted with Q2, we're going to end up with 0. And Q1, Q3, that's going to also give us a 0. And then finally, Q2 and Q3, when we dot those together, we're going to end up with twice the middle part and then -2 on the outside, because the middle entry in Q2 is twice the first and third entries. That's going to also be equal to 0. So we have an orthogonal matrix here, and MATLAB, just because this is the way it works, always gives us unit vectors for the eigenvectors. This is the situation that we have. Let's take a look at the determinants. Right? So D1 is the upper left determinant of S11. And D2 is equal to the determinant of S1:2, 1:2. It's the upper 2x2 matrix that's in there. And then finally, D3 is equal to the determinant of S1:3, 1:3. But that's the entirety of S. So let's take a look at these values. We already calculated these by hand. This is just verification that we've done that correctly. Then we know that pivot 1 is equal to D1. Pivot 2 is equal to D2 divided by D1. And pivot 3 is equal to D3 divided by D2. So we can see our upper left determinant values here and the resulting pivot values. So is that really the way it is? We're going to need the LU decomposition anyway. So here's LU is equal to, and I'm stomping on top of the L, so I should call this something different, but I'm going to just stick with our LU designation. So I've got LUS. And we can see here's the lower triangular matrix. And then here's our upper triangular matrix with the pivots are 6, 6.8333, and 5.2683. So all of these tests give us a means of finding that we have a positive definite symmetric matrix. And the way we actually talk about it is symmetric positive definite. So the last thing we want to do is go back to test number 3. We have this really powerful result, the fact that, hey, if S is symmetric and positive definite, there exists some A such that we can write A transpose A. Reviewing back to the LU decomposition, we know that any symmetric matrix, when we do the LU decomposition on it, we can write this as LUL transpose. And the upper triangular matrix U is actually a diagonal matrix, D. So we end up taking the pivots, and those are the values that are in our diagonal matrix D. So just from a graphical standpoint, we have a lower triangular matrix, and then we have a diagonal matrix, which is all zeros outside of the diagonal. And then we have L transpose, which of course is an upper triangular matrix. The way we're going to build the A matrix, because this is going to be A transpose times A, is we're going to build it using the diagonal matrix and L transpose. Specifically, and you can read through, he tells us this is the square root of D times L transpose, where the square root of the diagonal matrix is nothing more than the square root of all the entries in the diagonal matrix. So let's go back. We leave you to read through this example. So he provides a specific example here, and he gives us the representation for A. I want to go back to MATLAB and show you how we're going to do this here. So what we're going to do is we're going to write down L times D times L transpose, and let's just take a look at that. So if I set D is equal to the diagonal matrix of U, then what is L times D times L transpose? And so this is our question. What is L times D times L transpose? The diag command in MATLAB, remember, if you feed it a matrix, it will pull off the diagonal. So this is just going to pull off the pivots from the U matrix when we do the LU decomposition. And we have a problem doing multiplication. So it's pulled off D as a vector, but we now need to take that vector and build it back out to be so I'm going to call this pivots. And the D matrix is actually the diag of the pivots. This is a common occurrence in computer science. The diag command is what's called an overloaded function. So it does two things. When we feed it a matrix, it pulls off the diagonal elements as a vector. When we feed it a vector, it builds a square matrix with the vector elements on the diagonal. And we'll see that in just a second. So it pulled off the pivots. Then we take the pivots and we use those pivots to rebuild a diagonal matrix. So all we've done with the diagonal matrix is take our values here, and we can do that with the diag command. Use it once to get a vector, and then turn that vector back into a square matrix. And then we checked LDL transpose, which is this matrix right down here. So let me pull this up a little bit, make it a little bit easier to see. What we're going to do then is we're going to build this A matrix according to Strang. We're going to take the square root of D, and we're going to multiply by L transpose. And this is going to give us the matrix that is basically the separation of the symmetric matrix. So this is kind of like the square root of the symmetric matrix. Not quite, of course, but it's in that idea. Notice that it's upper triangular. It's not even a full matrix. This makes sense because what we're going to do is build a symmetric matrix, and the symmetric matrix does not have, a 3 by 3 symmetric matrix does not have 9 unknown values. It only has 6 unknown values. It has the 3 values on the diagonal, and then it has 3 values off the diagonal, but those are mirrored across the diagonal. So all the information we need is right here. So let's see if we can build S as A transpose times A. And this is our third test. Hey, we can do this, and that means that S is symmetric positive definite. We can't always, of course, do this back and forth, but we can in the case where we have a positive definite matrix. So that's just a demonstration. All right, some more things to talk about. We actually have several more topics to cover before we're done. The first item is the difference between positive definite and positive semi-definite. And he runs through a really nice set of examples here and comes up showing us graphical information, which turns out to be important when it comes to solving problems, which is what we're going to look at in just a minute. Positive definite matrix, we can think of it graphically as a paraboloid type of shape. So it could be elliptical. It doesn't have to be any specific type of paraboloid, but it's going to have some kind of a local minimum to it. And if it's quadratic, of course, that's going to be a global minimum. The case of positive semi-definite, we can have an infinite number of minimum values. And this is because the determinant is equal to 0. We have a singular matrix. So this is the set of examples that he's discussing. What I want to do is talk specifically about his conversation here and relate this to vector calculus. So this is a really important idea. It's used frequently, as we'll see at the very end of the video, when we talk about modern applications of linear algebra. So what we're going to do is we're going to leave you to read through this. It's very important to understand he is using, just to write down a quadratic type of equation in two variables, he's using this idea of x and y are the unknowns, and then we have some symmetric matrix here. It doesn't have to be a symmetric matrix, but in this case it is a symmetric matrix times xy. And of course, when we do this multiplication, we'll have an example in a little bit, we end up with some kind of a quadratic form. There's nothing to say that we couldn't have an xyz, and we could have 3 independent variables and come up with a quadratic form. This happens regularly, right? What we want to do is take a look at the gradient vector. Recall, given some function f, which is multivariate, And we're going to stick with 2 variables. It could be 3, it could be 4, it could be 5. In fact, he talks about 2 variables in the example, so I'll talk about 3. Then, when we want to talk about the rates of change associated with this function, of course, we go to the gradient. The gradient vector, and it's important to realize the gradient is a vector. It is going to be f partial with respect to x, f partial with respect to y, and f partial with respect to z. And if you're not familiar with that notation, we're talking about partial with respect to x of f, partial with respect to f of y, and partial of f with respect to z. It's the same thing. I'm going to use the shorthand notation here just because it makes things a little easier. So this is giving us rate of change information. But what we want in order to solve minimization problems is we need the second derivative. You remember from Calc 3, if you took it, the second derivative test. You even remember from Calc 2, in a single variable, we have a second derivative test. Well, in order to come up with that second derivative, we need to take the derivative of the gradient vector. We need the derivative, the gradient, if you will, of the gradient vector. And the way we calculate this is we take the gradient of, and we're going to write this out as a row vector, fx, fy, fz, and this is going to be equal to a 3 by 3 matrix. We're going to take the partial with respect to x across the entire top. So this is fxx, fxy, and fxz. Actually, I have those backwards. It's yx and then yz. Sorry, yx and then zx. And then partial with respect to y, fxy, fyy, and fzy. And then partial with respect to z, fxz, fyz, and fzz. This is the matrix that represents the second derivatives for some function with 3 independent variables. This is called the Hessian matrix. So the Hessian matrix is this rate of change of the rates of change. And this matrix, as long as we have sufficiently smooth f, you can see it's going to be symmetric. We have second partials with respect to x, y, and z along the diagonal, and then the off diagonal are the mixed partials, x, y, and yx, which Fubini's theorem tells us that as long as f is sufficiently smooth, those two things are equal to each other. And then xz and zx and yz and zy, those are all going to be equal to each other as long as we have a nice enough f function. This will help us determine what the minimum is for our function. And we can move this around and evaluate it at different locations to find different local minimum across the f function. This matrix is used in a lot of numerical solution methods for finding optimal solutions. Let me just make a note, right? We're always solving minimum problems because if we actually want to find the maximum, we just multiply by -1 and it becomes a minimization problem. So we always talk about minimization problems, but that really encompasses maximization as well as minimization. All right, so a little bit of a conversation here about positive semi-definite matrices. And this is, again, something you want to read through. Make sure you're comfortable with positive semi-definite, what it is and how it differs. And then what we want to do is we want to take a look at his example here with the ellipse. So I'm not going to go through the example that he provides. I have a different example up here, and I'm just going to take this and walk through some of the algebra so you can see what's happening. Let's take a look then. We end up with xy times, and I'll do this product. So we're going to have a vector, which is going to be a 2x plus 2y, and then a 2x plus 5y, and that's going to be equal to 1. Multiplying again, we're going to end up with 2x squared plus 2xy, and then plus 2xy plus 5y squared is equal to 1. Simplifying, we have 2x squared plus 4xy plus 5y squared is equal to 1. So that equation is the same as this equation right here. They represent the same thing. We could plot this ellipse. That would be no problem. But let's back up for a second and take a look at the diagonalization of this item here. This is symmetric. This matrix is guaranteed to have real numbers for its eigenvalues, and it's going to have orthogonal eigenvectors. Let's take a look. So I've started the process here of calculating the eigenvalues and the eigenvectors. Just as practice, obviously we could do this in MATLAB, and what we find is we have lambda 1 and lambda is equal to 6. So in the case where lambda is equal to 1, we're solving for the null space of 1, 2, 2, 4. X vector is equal to 0, and we can see that the eigenvector is going to be a minus 2, 1. And in the case where we have 6, similarly, we're going to have a negative 4, 2, and then a 2 and a negative 1 times x is equal to 0, and our second eigenvector is equal to 1, 2. And now we can come up with the diagonalization for our matrix. So the matrix 2, 2, 2, 5 can be written as the eigenvector matrix negative 2, 1, 1, 2 times 1, 0, 0, 6 times the transpose, which is the inverse. And so that's a negative 2, 1, 1, 2. Right? And this decomposition allows us to substitute in back up here and come up with a diagonalized version of the ellipse. So what we would do is we would take xy and we would multiply, and let me write it all. So what we have is we have xy times substituting in for the symmetric matrix here, and then xy as a column vector. Doing the multiplication, we end up with this situation here, and that's the same as Strang's example. And then what he says is that we have an obvious change of variables to take the ellipse that looks like this and turn it into something that's on the coordinate axes. So if we allow, for example, u to be equal to negative 2x plus y and v to be equal to x plus 2y, this is just a change of variables, just like a change of basis, really. Then what we're going to end up with is we're going to end up with uv times now a diagonal matrix, 1, 0, 0, 6, times uv equals 1. And so via the diagonalization and the properties of symmetric matrices, we're able to rewrite the ellipse in a fashion so that we have in the new coordinates rotated it onto the axis, just like we have here. So he uses capital X's and capital Y's. I use U and V's just because that's a more common structure than using the capital letters. But this is the idea of how he's working with the ellipses. I just wanted to run through that second example. All right, so one of the applications for using this whole idea of the gradient and the Hessian matrix has to do with machine learning and, in general, optimization problems. So now we start to get to look at the issues associated with just brute force linear algebra. GPT-4, which is the baseline for building ChatGPT along with most of the modern generative AI software, has 1.7 trillion parameters. So if we take a look at the gradient vector for the loss function or the objective function for ChatGPT, GPT-4, what we'll find is the gradient vector has 1.7 trillion components, entries. In order for us to use a lot of the optimization software, we're going to calculate the Hessian matrix. So the Hessian matrix has 1.7 trillion by 1.7 trillion entries. That's approximately 10 to the 24th entries. There are no modern computers that are able to do calculations in matrices that have 10 to the 24th entries. This is where a lot of the trimming down, the clever optimization techniques are applied, because we cannot simply brute force 10 to the 24th entries. We have to be clever about it. And this is where numerical analysis and linear algebra kind of come together. So one last comment here. This is the fact that all symmetric matrices are diagonalizable. We've already said this, but it's worth repeating. Right? We are always going to have a set of linearly independent eigenvectors. So recall back to the previous video, what we need for diagonalizability is a set of linearly independent eigenvectors, and we're always going to have that with our symmetric matrix. So symmetric matrices are extremely powerful, and symmetric positive definite matrices even more so. And what we'd like to know is, we'd like to know what is the means that we can kind of guarantee that we have the situation. And that's what we're going to be talking about in chapter 7. Before we go, let's take a look at the questions for today. So these are the discussion questions. Basically just working through some of the items that we covered in the video. Thanks very much. We look forward to seeing you in class.